This is part 2 of geometry on beginning concepts of triangles. Let's talk here about things that you can do with the triangle in the coordinate plane. Okay, here we have a triangle, 3 random points that are connected to make a triangle. We can see that we can find different things about them. We can use the distance formula if we want to use the coordinates, or actually it's probably easier if it's already in the coordinate plane to put a box around it, since the coordinate plane is all parallel and perpendicular. You can make lots of right triangles and just use the Pythagorean Theorem, a squared plus b squared equals c squared, and solve for it, which we've done here. Usually at this point you can tell pretty quickly if it's going to be equal length sides. 8 and 3, it's going to be 3 squared plus 8 squared. Take the square root. Over here 4 and 7, you can tell just by looking that it's not going to be the same thing. Here it's written out. You know it's not going to be the same. They don't have the same factors, so it's not going to work. And the same deal up here with 10 and 4. 10 and 4 for your side length. So again, a squared plus b squared equals c squared. Be sure you notice that in each case, the side of the triangle is the hypotenuse of a right triangle. So we're using the Pythagorean Theorem. And you can get a real quick reaction as to what it's going to be and tell what most of it is. Now, if you need to know whether they're perpendicular, in other words, whether it's a right triangle, then look at the slope. So also by drawing the box around it in this fashion, you can get the slope very easily. The slope of this section is rise of 4, run of 10, or 2, 5. And again, for each one of them, the slope is 8 thirds, 8 over 3, and the slope here is negative 4 over 7. Remembering, of course, from algebra that lines are perpendicular when their slopes are negative reciprocals. None of these are negative reciprocals. This is not a right triangle. And it's scaling because the side lengths are square root of 65, square root of 73, and square root of 116. Another example. Here is one that is isosceles, and it's acute. We've done the same thing. Notice that 2 are the same length. It's 4 and 10, 4 and 10. Pretty obvious that they're going to be the same. You try the slopes. Find out that none of them are the negative reciprocal, so it is not a right isosceles, a triangle. It is an acute isosceles triangle. You can usually spot if they're going to be isosceles. This one is a little bit more problematic just because so you'll be aware that this sort of thing happens. Here, the top line up here, length is the square root of 153. Its components were 3 and 12. Down here, this one is also square root of 153, and it was 8 and 9 for the components. Those have the same prime factors. So if you spotted that, you would know what was going to happen once you did it, that the prime factors are arranged differently between 3 and 12 than they are between 9 and 8, but they're the same factors. So you come up with a square root of 153 for each one of them. So this is acute isosceles. The other one's different, just a little bit. And you maybe a little helpful hint to make sure you watch out for it. So what can you do with these on the coordinate plane? You can pretty easily find the slope of each one of them. If it's a negative reciprocal, then it's a right angle. You can very easily find pretty quickly, without even calculating it, whether or not they're going to be the same length, as long as you're watching out and you're careful. Next thing up, you're going to need a little piece of paper. So get yourself a little piece of paper, and on this little piece of paper, at 3 sides of the 4, make a dot. I'm just going to make a dot there, right on the edge, and I'm going to make a dot there, and I'm going to make a dot there. Doesn't matter where they are, just make some dots. Take a straight edge and connect the dots to make a triangle. Oh, let's call it something interesting. I already did dog and cat. How about a kid's name? Ben. This is going to be Triangle Ben. Benjamin for Benjamin Franklin. There we go. Triangle Ben. In your cipher, draw a horizontal line with some room either on top of it or on bottom of it. I'm going to do my stuff on top. A horizontal line across the page with some room above or below. About in the middle, put a dot. Doesn't have to be exactly in the middle. So once you've got that done, we're going to tear up our triangle. Tear it in such a fashion that the angles are all intact. So I'll tear down the middle. There's my angle B. And then I'll do my angle N and E right here. And the extra paper doesn't matter. So there's my triangle Ben, torn up. So tear yours up, or if you won't cut it, it doesn't really matter. Take any one of the angles, it doesn't matter. I'm going to take B. Going to glue it down so that the vertex is on my point, on my line, and the line is collinear with the line that you drew, right on top of it. So there's angle B. Once you've done that, go ahead and take one of the others. I'm going to take E. Do it facing the other direction. Put the vertex at the dot that you've made and line it up with the line. Now the next one, you're going to have to be a little bit careful. Maybe get off some of the extra paper here that's next to your angle near it. So the point's kind of out there by itself. And we're going to paste it on. And look what happens. It fits exactly. Did you get it? Oh, not quite. There we go. I'll make it a little shorter so you can see. The point at the same place and the lines lined up. And it works. Here we have angle B, angle E, and angle N, all together here on the line. I'm looking at this and I'm thinking, you know that's a line. It's a line. And a line, I'm pretty sure, because we just had a lesson on, a unit on lines, is 180 degrees. A line is a straight angle with its vertex there. That's 180 degrees. So what do we have? We have angle B plus the measure of angle B plus the measure of angle E plus the measure of angle N is, wait for it, 180 degrees. Wow. Woo. And that just happens to be the triangle sum theorem. Again, we're going back and proving all of the basics, demonstrating all the basics to make sure we know what we're doing. So there we've demonstrated by tearing the paper and putting it together that the three angles together make 180 degrees. Okay, let's work a little bit on proving it. If they're in your cipher, you would please draw two parallel lines with some room in between them to make a triangle. So we'll call parallel, means it has the same angle on it, means it's parallel. So these are parallel lines. I will draw a transversal, making some angles. Then I'll draw another transversal that has the same intersection with the top one as the other one. And I've got a triangle. I'm going to label this one. What's this one going to be? I think maybe Ollie or Ole. My dog's name is Ollie, but that's not how you spell it. So we'll say Ole, O-L-E. Okay, what can we do about this? Well, if I look up here, I can call this one O prime. And what's the relationship between O prime and O? They are alternate interior angles. Since the lines are parallel, they are congruent. So I can mark them as the same. Here I have angle L. This will be angle L prime. Oh, look, they're alternate interior angles, and the lines are still parallel, so they're congruent. So L and L prime are congruent. Right, this up here is still a line. We just did this line thing. That's 180 degrees. It's a straight angle with its vertex there. So what we can say here is that the measure of angle O prime plus the measure of angle E plus the measure of angle L prime is 180 degrees. From there, it's a simple matter to substitute in. As we just mentioned, L and L prime are the same, so I can substitute in L here. O and O prime are the same, so I can substitute O in here, and I will have that the measure of the three angles of the triangle add to 180 degrees. We've demonstrated it by tearing the paper, and we've proven it for all triangles with our little short proof here. A corollary. A corollary. What's a corollary? We got a new term here. Corollary. A corollary is a theorem that follows directly from another theorem. It's kind of like the next step, but we use it so much that it gets its own name. And since I'm an American and since I'm in Texas, I say corollary. My grandmother, who was from England, Weston-super-Mare on the West Coast, would very likely, if she talked about it, say corollary. People on the other side of the pond, the Atlantic Ocean, tend to say corollary, the Europeans, and people on this side of the pond, the Americans and others, tend to say corollary. Okay, so a corollary is a theorem that follows directly from another theorem. And we just happen to have one of those here, and it is the corollary to the triangle sum theorem. The acute angles of a right triangle are complementary. How is that a corollary? Well, it's just kind of like the next step. The one that we just proved said that all three add to 180. So if one is given as 90 degrees, subtract 90 from both sides of your equation, and you'll get that the other two must equal 90. So that's the corollary to the triangle sum theorem. And we're going to pause right here for a moment and come back for part 3.